4.6 is a summary of curve sketching. And when we're in school, I will be giving you an equation, some sort of function. It may be a polynomial, it may be a rational function, but I'm going to give you a function, and I would expect you, without the help of your graphing calculator at all, so without any kind of visual aid to give you any idea of what that graph might look like, I would expect you to be able to find some really key points on that graph and sketch a graph of that. So not by making a t-chart, but just by kind of finding key points on a graph, maxes, mins, intercepts, knowing what the domain or range is, any asymptotes there are. So that's what this section is all about, is a summary of all that stuff that you've learned about curve sketching, and this goes back to even Algebra 2. Let's get started. So first of all, for each of these, I would challenge you to pause the video before I start writing down for each of these, and you write down what you think, how you think you would find each of these things. So if we start with x-intercepts, how do you find your x-intercepts? Well, x-intercepts is where it crosses the x-axis, so these always occur when y equals 0. So we need to be able to solve the function when y equals 0. So we would set the function equal to 0 and solve it. Some examples of things you might do: if it was a polynomial, you would factor it. You could use the quadratic formula. If it's a rational function, well, that just means there's a numerator and denominator, so fraction can only be equal to 0 if the numerator is equal to 0. So if it's a rational function, you would set the numerator equal to 0 and then solve that one. All right, let's move on to y-intercepts. How do you find y-intercepts? Well, if you think about y-intercepts, that's where it crosses the y-axis, so my x-coordinate is 0. These are a lot easier usually, because these occur when x equals 0. So since a lot of times you have explicit functions written y equals, you're just going to let x equal 0 and simplify it. The domain and range. How do you determine the domain and range? Well, keep in mind that the domain is the x values and the y is, or the range is the y values. You usually need to think about the domain before you can determine the range, or a lot of times if you can figure out the domain, then it's pretty simple to figure out the range by plugging in those extreme domain values. So you're thinking about what x values for which a function can be defined. So you're thinking more about what values must be excluded. So what are some things that might have exclusions? Well, if you're dealing with a square root, you can't take the square root of a negative number, so that's going to limit your domain. If you have a rational expression, you can't have your denominator equal to 0. That would be another way that values could be excluded. And sometimes you just need to think about the context of a word problem. So just in context, are there any values that couldn't be included? So that's just some examples of how you might determine what the domain and range are. Continuity. We have to think about continuity. Can you think back to chapter 2? We talked about continuity. There were 3 things that had to exist in order for a function that can be continuous. Can you remember what those are? First of all, f of c is defined. In other words, any value in the domain is defined. It has a y value. It has a range value. The second thing is that the limit as x approaches c of f of x has to exist. In other words, if I'm approaching that value c from the left and I'm approaching from the right, I have to have the same value. So in other words, remember an example of discontinuity would be jump discontinuity. So f of c could be defined, but if there's jump discontinuity, then the limit doesn't exist. The limit as it approaches from the left and the right doesn't exist. And then finally, the last thing is the limit as x approaches c of f of x has to equal f of c. Again, we're approaching from the left and the right, but there can't be a hole there. If there's a hole, then it's obviously not continuous. So that's what we're doing with continuity. We have to make sure that functions are continuous. Functions that are continuous at every point in their domain, first of all, are all polynomials. All polynomials are continuous. All rational expressions are continuous in their domain. Keep in mind, If there's an asymptote, if it's not defined someplace, then that value is not part of its domain. But within the domain of a rational function, every point it's continuous at. Radical functions, again, there are values at which it's not defined, where it doesn't exist. If we're taking a square root of a negative number, we can't do that, so it wouldn't be in their domain. Trigonometric functions, again, in their domain, they are continuous. Some of them, they have asymptotes. Those asymptotes are not part of their domain. Exponential functions and logarithmic functions. These are all continuous functions. All right, next up, vertical asymptotes. How do you find and when do vertical asymptotes occur? They only occur in rational functions, and they only occur if the rational function is undefined. So in other words, how would you find it? You would find it by setting the denominator equal to 0 and solving for x. Therefore, remember that not all rational functions have vertical asymptotes. If I have on my denominator x squared plus 1, there is no place that that function is not going to be defined. The end behavior. The end behavior is what happens to the function as x approaches positive infinity or x approaches negative infinity. Perhaps you remember, those of you that had me for Algebra 2, for polynomials, remember the end behavior dance that we used to do. Our end behavior dance, remember the leading coefficient determines whether the right end of the graph goes up or down, and the degree determines if the negative or left end of the graph goes up or down. For a rational function, remember you're just looking for the horizontal asymptotes. Are there any horizontal asymptotes? And that's basically your end behavior. And that brings us to our horizontal asymptotes. How do we determine whether we have horizontal asymptotes? Again, remember that horizontal asymptotes only occur in rational functions. So we are going to look at and compare the degree of the numerator to the degree of the denominator. So there's 3 cases that we have for that. The degree of the numerator being less than the denominator, the degree of the numerator being equal to the degree of the denominator, or the degree of the numerator being greater than the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then as x gets really, really, really large, y is going to approach 0. If the degree of the numerator and the degree of the denominator are equal, your horizontal asymptote is going to be y equals the ratio of those leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. How do we find slant asymptotes, and when do they occur? Slant asymptotes occur if the degree of the numerator is exactly 1 more than the degree of the denominator. And then the way that you're going to find them is by using long division. And when you use long division, you use just the whole divisors. You ignore any of the remainder. Relative extrema. How do you find those maximums and minimums? These last 3 are the ones that are most recent. We've just learned these. Everything up above we've either learned in Algebra 2 or in the beginning of calculus. So how do you find the relative extrema? We're going to use the first derivative test. So now we just need to kind of write down the steps of the first derivative test. Step 1, find the critical numbers. So we need to find the first derivative, set it equal to 0, find when it's equal to 0 or undefined. Second thing is, with those critical numbers, you're going to make a labeled sign chart, and you're going to test points in the intervals between those critical numbers. Then finally, if it goes from increasing to decreasing, or positive to negative, you know you found a relative max. If it goes from decreasing to increasing, or negative to positive, you found a relative min. Almost done. How do we find points of inflection? Again, this is something that's relatively new. We find points of inflection by setting the second derivative of the function equal to 0, or undefined. And what do they tell us? They tell us that the concavity changes at those inflection points. And finally, how do we determine the concavity of our function, of our original function? And again, this is where we use our second derivative test. So go ahead and write down those steps for the second derivative test. The first thing we do is find our possible inflection points. So that's where our second derivative is equal to 0 or undefined. Then you're going to make a labeled sign chart with the critical numbers and the inflection points. This actually can help you determine the relative extrema. If you want to skip the first derivative test, you can go right to the second derivative test to determine the maxes and mins and the concavity. And finally, when you test those critical values, if you get a positive value in the second derivative, it's going to be concave up, which means you're going to have a relative minimum. And if it's less than 0, it's going to be concave down, which means you have a relative maximum. So now if I give you a function, you should be able to go through any of these and graph that function. The other thing you should be able to do is if I give you clues about the graph, you should be able to graph a sketchy curve that meets all of those requirements. If you have any questions, I look forward to seeing you in class.